Good afternoon, everybody. And you must be noticing my dress. It is due to the pandemic situation since I am in the office. So I am going to introduce Professor Somnath Dasgupta, who has been awarded a lectureship in the name of Sesquicentennial Commemorative Award, alternately gold medal, and the next year it's a lectureship. So this year Professor Dasgupta has been awarded the lectureship for the 2019, and this has been possible due to a generous fund provided by the Secretary of the Geological Survey of India, their 150 years felicitation committee, who provided us 3,71,200 and some rupees in the year 2003, and then we have instituted this endowment. Now, Professor Somnath Dasgupta, currently INSA senior scientist at IISER Kolkata, served as geologist in Geological Survey of India, as professor in Jadavpur University, as professor at IISER Kolkata, as vice chancellor Assam University, and as Ford Foundation chair professor at Jamia Millia Islamia. He obtained his PhD degree from Jadavpur University in 1979. He is a fellow of all the 3 National Science Academies of India and of World Academy of Sciences, TRIST. He is a recipient of N.N. Chatterjee Medal from Asiatic Society, National Mineral Award from the Ministry of Mines, Krishnan Medal from the Indian Geophysical Union, and J.C. Bose National Fellowship from DST. He is a fellow of the Alexander von Humboldt Foundation and served as visiting professor at Ruhr University, Germany, and Hokkaido University, Japan. I welcome Professor Dasgupta on this occasion, and now it is his turn to talk.
Good morning. At the outset, I am thankful to the Asiatic Society for conferring me this award. It would have been obviously better to talk in person, but however, this is not possible at the present time. I am Somnath Dasgupta. I have superannuated from Indian Institute of Science Education and Research, Kolkata, and At present, I am associated with the same institute in the capacity of an INSA senior scientist. Most of the work that I am going to present here was carried out during my tenure at Jadavpur University. I have tried to be as non-technical as possible in the presentation to make it easily understandable for non-specialists. Let us now move forward to the actual presentation, and for that I will use a PowerPoint presentation. The title of the talk is A Tale of Three Supercontinents, the Indian Connection. The first slide shows you two pictures. On the left is that of the Eastern Ghat Belt, which is on the east coast of India, covering the states of Odisha and Andhra Pradesh. And on the right side is the familiar picture from Antarctica. Part of this story is how we decided that these two contrasting areas were together at some point of time in the past as constituents of what we call supercontinents, continents joined together without intervening oceans. Everything started with this gentleman. In 1915, the German meteorologist and geophysicist Alfred Wegener proposed the hypothesis of continental drift, in which he postulated that a single supercontinent Pangaea existed, which later broke down and the fragmented landmasses drifted to their present position. Wegener based his hypothesis on the basis of the observations that he had, for example, jigsaw-like fit of the continents, global distribution of fossils, climatic signatures, similar rocks across continents, and continuous mountain ranges. On the left of this slide, I show you a diagram which shows why Wegener thought about jigsaw puzzle fit of the continents. You can see how South America and Africa can be joined together and how nicely they fit together. This was the original configuration of Pangaea that Wegener visualized, and then the Pangaea broke down and the continents moved in different directions, leading to the present position. Pangaea is thought to have formed around 300 million years ago. Then came in 1960s the revolution in earth sciences, which we call plate tectonics. Plate tectonics showed that not only the continents move, but a portion of the earth below, which is known as lithosphere, which has a thickness of 100 to 150 kilometers, move. And also there are oceanic plates and the seafloor spreads pushing the continents. This is the current disposition of the plates as of today, and as you can see, some of the plates are entirely oceanic, like the Pacific plate, and some of the plates are entirely continental, like this. Now these plates are in constant motion with respect to each other. And obviously the plates have boundaries. Now we have three types of plate boundaries, which are called as first the divergent plate boundary, where the plates diverge from each other. Example of this boundary will be the mid-oceanic ridges that we have in the modern oceans, like mid-Atlantic ridge. The second type of boundary is the convergent boundaries, where the plates approach each other or converge, and then one of the plates go down under the other, and the process is known as subduction. The third boundary is called transform boundary, where the plates do not diverge or converge, but they simply slide past each other. For example, the San Andreas Fault in California. Now I will introduce the term about which this particular talk is based, that's the supercontinent cycle. The history of the Earth has been punctuated by formation and destruction of several supercontinents, which are simply amalgamation of the continents without any intervening oceans. And this cycle is known as the supercontinent cycle. Supercontinents form by destruction of ocean basins in between by a process of subduction, which I have introduced in the previous slide. And then when the ocean is consumed, then we have a continent-continent collision. Supercontinents break up because formation of deep fractures, which we call rifts, beneath the continents, and then these continental blocks get separated. At present, for example, the African continent is being divided due to the formation of the Red Sea rift. This is a summary of the continents in the last 3 billion years in the history of the Earth. We have several supercontinents, but in this talk we will talk about 3, and these 3 are Colombia, Rodinia, and Gondwana. So these are the 3 continents we will talk about in this talk. Now, the question is, how do we carry out intercontinental correlation? The logic is very simple actually. If 2 continents were together at a particular time, they will share the same geological history. And by that, what we mean, the rocks on both sides should be similar. The rocks should have similar age. The rocks should show the coordinates of the magnetic poles very similar. And then if there are fossils, then there should be similarity in the fossils. So all we have to establish is that the 2 continents share same geological history, although they may be now situated 5,000 kilometers away. For example, India and Antarctica. Now, how do we get the timing that I mentioned in the last slide? This is done by a method which we call geochronology. And here we use the radioactive decay scheme of different radioactive elements like uranium lead, rubidium strontium, samarium neodymium, lutetium hafnium, rhenium osmium, and so on. I am showing figures of 2 photographs of 2 minerals, which one is zircon, which is a zirconium silicate, and a monazite, which is a phosphate mineral. The images show nice zoning displayed by these minerals. Both of these minerals contain uranium, lead, and thorium, and therefore they are completely datable using the radioactive decay schemes, and we know the half-life of these uranium lead system very clearly, so we know that they can date very older events in the Earth's history. Let me now introduce the first supercontinent that I was talking about, the supercontinent of Colombia. This is the general configuration postulated by these workers. And the supercontinent Colombia formed around 2100 million years ago and broke down at 1600 million years ago. This is the relationship between India and its neighbors at that time in the part of Colombia. So you can see India was supposedly close to North China and East Antarctica. There are some amount of uncertainties in the configuration because of the very old age. However, in case of Rodinia, which assembled at 1000 million years ago and broke down at 700 million years ago, the configuration is much more clear. And here you can see that during the Rodinia time, India, South Africa, Australia, and coastal areas of East Antarctica formed a continuous continental block. And this was close to East Antarctica, close to North America, Europe, and all together they formed the supercontinent of Rodinia. The last supercontinent that we have in the Earth's history was the Pangaea. That was one that Wagner proposed long back, which assembled around 300 million years ago and started to break 200 million years ago. But we will not talk about Pangaea in this particular presentation. We will talk about Colombia, Rodinia, and Gondwana, which Gondwana formed around 500 million years from now. This is what is known as the tectonic divisions of India. And this is the Eastern Ghats belt, which runs from near Bhubaneswar down to Nellore in Andhra Pradesh. And these buff-colored places are the stable parts of the Indian shield. And I will just request you to remember about this name, the Dharwar Craton. A craton, by definition, is the stable part of the very old part of the continents. And Dharwar Craton, just to give you a geographic significance, the city of Bengaluru is located within the Dharwar Craton. And we will come back and talk about Dharwar Craton in the next slides. So please remember this and the Eastern Ghats belt. The rest of the part are not important right now. So this is the Eastern Ghats belt and what we say a geological map of the Eastern Ghats belt after these workers. All these rocks are metamorphic rocks. Therefore, these are changed rocks. They were originally sedimentary rocks or igneous rocks. Now, as you can see that these metamorphic rocks are not of the same type all along the belt, but you have different kinds of rocks which are demarcated by different symbols, and these rocks are arranged in a sort of longitudinal subbelts. That is the geological map of the Eastern Ghats belt. But the picture changes considerably if we look at the time of the original formation of these rocks, the changed rocks. And this is determined by neodymium isotopic composition. And when we have these data, then we see that the belt is divided not only longitudinally, but also transversely. For example, I will go back to the previous slide where please look at this particular portion which is shown with a single symbol. But if we go here, you can see that this is divided into two parts. One is the green part and the other is the buff colored part. And each of these blocks have different ages of formation, which we call the neodymium model ages. And on the basis of that, we divide the Eastern Ghats belt into these domains, which we call isotopic domains, because they were distinguished on the basis of isotopes. Now, what did we do? Over a period of nearly 20 years, we determined the history of changes in rocks from each and every isotopic domain from numerous places in the Eastern Ghats belt. Since these changes are metamorphic and caused by changes of pressure and temperature with time, we essentially determined PT, time history of evolution of the rocks. The principle lies in application of equilibrium thermodynamics to calculate pressure and temperature, and application of uranium-late thorium decay equations to calculate the timing of those changes. These we call PT paths of evolution of metamorphic rocks at different time. The determined PTT paths, the small t stands for time, from the isotopic domains are shown in the next slide. And these can be compared with similar paths reported from other continental fragments that were supposedly together at some point of time. and now they are separated. The idea is again simple, is that if these were together, they should have similar PTT paths. This is the picture of the compilation of the PTT paths of the different isotopic domains I talked about, each shown by a different color. Now you can see very clearly that different domains were metamorphosed or changed at different times. You can see the ages which are shown here in million years. And at different pressures, you can see this is the y-axis is the pressure, and different temperatures which is shown in the x-axis. So the apparently continuous Eastern Ghat belt, which runs from Bhubaneswar to Nellore, consists of different fragments that have separate geological evolutionary history, and that is why they have different pressure, temperature, time paths. Now each of these different histories can be compared with other continental fragments. We particularly compare with the results from East Antarctica. Now I am going back to that isotopic division of the Eastern Ghats belt, and now I will describe the geological evolution of the different segments of the belt. We start with this purple color portion, which is the domain 1A nomenclature. Name of this is domain 1A, and we look at the history of evolution of the domain 1. This domain 1 was, as you can see, was formed due to the collision of the Dharwar Craton of India and East Antarctica at around 1800 million years ago, and this amalgamation was complete by 1540 million years ago, forming a single continent. And this red portion is the domain 1A, which formed in between the Dharwar Craton, that is India, and East Antarctica blocks. And so at the end of 1540 million years ago, we have a composite block of India, portion of India, that is the Dharwar Craton, and the east parts of East Antarctica, and with the domain 1 of the Eastern Ghats belt. This is how we visualize that the domain 1 here was connected with the trans-North China orogenic belt here, along with the Capricorn belt in Australia. They have similar geological evolutionary history, and as you can see, India was close to East Antarctica, Australia, and North China at that time, around 1540 million years ago. Now, going back to that isotopic division slide, and we will focus on this green area, which is the domain 2. The domain 2 was formed by a renewed collision between the India block, that is the Dharwar Craton, along with the domain 1 of the Eastern Ghats with East Antarctica. This cartoon shows the stages of development of a composite block at the end of formation of Rodinia. Now the domain 1 of the Eastern Ghats was a part of India at the end of 1540 million years. This enlarged India then collided with another part of East Antarctica at around 1500 million years ago. This collision went on for 500 million years, and finally amalgamation of all the continental blocks took place at around 900 million years as a part of Rodinia, the next supercontinent. So Colombia broke down and then Rodinia assembled after 500 million years. So you can see now we have the Eastern Ghats domain 2, the Eastern Ghats domain 1, which was part of Dharwar Craton and a part of East Antarctica, all joined together in the form of one single continent. This is how Rodinia looked 900 million years ago, according to these authors. And as you can see, this is the greater India. India has taken almost its shape, and it was connected with East Antarctica and with the other parts of the world in the component of Rodinia. As you can see, all the continental blocks are assembled at one place. And so this is how Rodinia looked like 900 million years ago. So it is not only the Rodinia, the important part here is to mention that the Indian landmass as we see today, excepting the Deccan Plateau, which was formed at a much later age, most of the other part of India assembled between 1000 and 900 million years ago. So not only the Eastern Ghats and Antarctica, but also a large part of India joined together at this time, which we call Greater Indian Landmass. And so India took its almost the present shape, other than a portion of the Deccan volcanics. But then Rodinia broke up 700 million years back. So before we go into that breakup story, we go back to the slide of the division of the Eastern Ghats belt, and now we look at this buff-colored region, which is the domain 3 in the classification scheme. This domain is surprisingly, we think that this was not a part of India at around 900 million years as part of Rodinia. It was a part of East Antarctica at that time, precisely speaking, the South Prince Charles Mountain range of East Antarctica. And then, at around 500 million years, this block then came together and collided with the Greater Indian landmass to form part of a total form of the East Gondwana. So, the part which was this part which contains the Chilika Lake area was possibly not a part of India before 500 million years ago. This joined India at around 500 million years. Now, how did we come to this conclusion? Because the geological evolution of this block of the domain 3 does not match with that of the domain 2 or domain 1. So they do not share the common geological history, but they share a common geological history with East Antarctica, part of East Antarctica at that time. So they were possibly together, and after the final amalgamation took place between East Antarctic block and the Indian block at around 500 million years, all of them came together and India was formed. But as I said, not the Deccan volcanics. This is how we look at the Gondwana reconstruction at 500 million years. As you can see, India was very close to Madagascar, Sri Lanka and Antarctica. All were close together at that particular point of time. India and Madagascar share absolutely similar geological evolution, particularly the southern part of India and Madagascar. Southern part of India and Sri Lanka, they have absolutely similar geological evolutionary history at 500 million years. So they were together as part of the supercontinent of Gondwana at around 500 million years. Now, the summary of the talk is that using the Eastern Ghats belt as a prototype, I have documented birth and demise of 3 supercontinents, namely Colombia, Rodinia and Gondwana, covering a period of approximately 1600 million years. Now you may recall the total history of the Earth is around 4,600 million years. So this Eastern Ghats belt records the history of 1600 million years of that total part of the Earth's history. Different parts of Eastern Ghats were connected with East Antarctica at different times. A large part of the present-day crustal architecture of India was formed 1,000 million years or 900 million years ago as a part of Rodinia, but the area around Chilika Lake probably joined 500 million years ago. Although I have not discussed here, we all know that the last major amalgamation took place at about 50 million years ago when India joined Eurasia along with the formation of the Himalayas. Therefore, the supercontinent cycle continues. Thank you very much for your patience. Now, I once again thank the Asiatic Society for conferring this lectureship award to me. My research was supported by DST, CSIR, Alexander von Humboldt Foundation, National Science Foundation USA, Japan Society of Promotion of Science, and German Research Foundation. Nothing would have been possible without the involvement of my doctoral, postdoctoral, and master's students. I am ever indebted to them. All in my family stood by me all through and helped me to achieve these goals. Thank you very much once again.